All right, in this screencast, I'll be generalizing Mira to prediction. We'll do a little bit that's specific to structured prediction as well. So first of all, we'll do one best Mira. So this is just Mira applied to prediction. And so imagine that we're in the process of doing Mira, and right now our vector is v1. Okay? And so whatever we're doing, we'll find that this is the best solution, right? If we're doing tagging, maybe we do our Viterbi algorithm using the current vector, and we find that the best y is this. The correct y is this one, right? And so we pick the wrong one. And so with one best Mira, what we're going to do is we're going to do an update. We're going to say, okay, we picked this one. We wanted to pick this one, so we'll take the vector in that direction. And this is basically the update that we've been doing. So first of all, we subtract off any component that we don't want, and then we add the margin that we want. We subtract off the parallel component of v1, and then we add the margin that we want. So overall, v2 will have the margin that we want. And so I'm going to do a few examples of v2. So let me copy this. So it really depends. What happens next depends on what margin we want. So v2, example 1. So let's say that we want a large margin, and so after, first of all, we want it to be perpendicular. So I make it perpendicular. That would be this part, subtracting off the parallel part, and then I add the margin. So I've got my perpendicular vector, and then I add a certain multiple in that direction. Now let's say that this is quite large. Okay, so this is just my gamma d hat. And so overall, this here is going to be my v2. Okay? And so then we do our Viterbi algorithm or whatnot, and we find that now, let's say now this is the best one. It's a pretty close call between those two, I'd say. So I'll call this y, maybe y2. I'll put the 2 down there. Call that y2, and so then we're going to do another update. Since this will be our d vector 2, and so we might update it back and forth for a while, right? At each step, we've updated our vector, so we're going to have to do our Viterbi to get the new best one, and we might do a bunch of updates, and this is just one example, right? So we need a bunch of updates for a single example before the correct solution. I guess the correct, yeah, whatever it is. Correct prediction is returned. Now, I'm going to ask a question about this later. There's something that Mira is supposed to do that it might not do in this case. And I guess I'll ask that as the question. What is Mira doing here? Not doing here that it is supposed to do. So we carry on. We're going to add a multiple of that vector. And this vector is kind of going to go back and forth until eventually it's picking the correct one. But what is it not doing? I'll leave you with that question. I'm going to do a different example where we've got, so this is example 1 with a large gamma. Really, it's that gamma was large relative, I guess, gamma times the, gamma was large relative to the size of the original vector. And so in my next example, I'll be doing V2 again. Yeah. This will be example 2 with a small gamma. Okay. So I'll just copy some of this here. Okay, so first of all, we're going to do the same update. We make it perpendicular, so we get that vector. And then we're going to add a multiple of this to get the margin we want. In this case, I'm just going to add a much smaller multiple. Something like that. So now we're going to get a vector in that direction. So this will be our V2 now. And this small vector here is gamma, oops, that's gamma d hat. Okay, so then we do so then we're going to do our Viterbi or whatnot to get the best solution, and I think the best solution is now this one, which is the whole point of changing the stuff. And so we get this as the best solution, and so of course, since it's the best solution, we're not trying to create any margin with it, and we have no other points to compare to, so we stop here, right? We stop here. My question is, did we ensure that we had a minimum margin of gamma? And the answer is, of course, no. No, because when we got the right prediction, we had no other point to compare it to check if the margin was big enough. Yeah. Yeah, so we don't get a minimum margin. And that's exactly what could go on here. It might go back and forth for a while, and then eventually it's predicting the right one. And then again, we haven't made sure that we have the margin that we want. It's not predicting. It's not ensuring a margin of. So we can't just look for the best solution all the time, unless we don't care about having a margin. If we want to have a margin, then we're going to have to look at more than the best one so that we can compare with, say, this point and this point. In fact, so we can see if we did the best two, so two best Mira, I'll say this should work with enough updates. I'm pretty sure, right? Because we can see, even when we're predicting the best one, if we use the best two method, we'll find that one that's pretty close. And if it's too close, we'll still do an update, and we'll keep doing updates until this vector gets big enough that we have the margin we want with respect to both of the points. But we'll have to keep doing our viterbi to get the best point over and over again. And a lot of the updates are mostly undoing each other. So what's going to be a better solution, though, is we're going to do more than 2. We're going to do the best k Mira. So k would probably be a number bigger than 2. And so in this case, since we're only in 2 dimensions, basically we'd need the best 3 Mira. So that we get this point, and then we can make sure that the correct solution is separated from both of these points by a sufficient margin. So basically we take the top k solutions and make sure we have the margin we want with respect to all of them. Now, when we predicted this and we wanted that one, well, we just made an update in this direction. But now if we've, I want to copy this picture. So let's do an example. I.e., this will be the top or 5 best Mira. Okay, and so the 5 best Mira are going to be the correct one, this incorrect one, this incorrect one, I think this incorrect one, and that incorrect one. Right? So we get the one that we want, and we get 4 other ones. We want the margin to be large enough. And so, okay, well, these two actually probably don't really matter. The margin is really going to be determined by these two. And we don't really want to do an update in that direction or in that direction. We want to kind of do updates, well, so let's use another color here. Just use blue. Let's draw a line like this. So from support vector machines, I might call these like these two the supporting points. And so basically, we want to make, in this case, where all the losses are the same, if you know what the losses are, that's the next thing I'm going to go into. We want to make this distance as big as possible. Or, sorry, we want to take, because we don't want to make the distance, we want to make the margin with respect to both of these points the same, because the loss is the same. So really, we're going to want our vector to be perpendicular to this plane. In this case, it's a line in 2 dimensions, but in general, this would be a plane, depending on how many points there are, some kind of hyperplane. So first of all, we could find the components of V that are parallel to this line and subtract that off. So that's the parallel component. So now we've got just the perpendicular component. But wait a minute, if we do that, maybe we don't want to do that, because maybe pointing in this direction is working well for other sentences, right? So maybe we don't want to do that. Really, we want to change this vector as little as possible while making the margin, which basically, for the margin, we only care about the component of B in this direction to maximize it with respect to both. We want to make that margin as big as possible. So I'll call this here. So we don't want to use that. anymore. So I'll call this here d vector. So we want to change v as little as possible in the direction of, well, we want to change it as little as possible while getting the largest margin possible. Okay, so to change it as little as possible, ideally, we just want to hold on a sec. Okay, so while getting the, not the largest margin possible, the margin as large as required, right? Which basically means, yeah, we want more updates in that direction, but since this already tends to be more towards this direction, the margin for this one is maybe pretty much big enough. So actually we might want our update to be a little bit more in that direction. So it's increasing this one a little, the margin for that point a bit more than the margin for that one. So it seems like it could be a fairly complicated problem. So let's just state this as a minimization problem. i.e., we want to minimize of our update minimize of v2 minus v1 given this constraint such that v2 dot y minus v2 dot yk. So by yk I mean one of all these points, obviously not the same one, is greater than my margin for all yk not equal to y, right? Yeah, so I think that's pretty much what we want. Yep, this is what we want. I just checked. Cool. So I'll call this all best Mira. Now, ideally, we wouldn't just pick the top 5 points, because maybe when we're working in very high dimensions, we need more than 5, right? So ideally, we would use all the solutions, right? But I guess usually only the top few will affect the update. I'm not sure how many. I'm not sure if it's 10 or 100. But apparently, the paper says that you don't need too many, which I think kind of makes sense. There's going to be lots of really bad solutions. So once you've trained your algorithm a little bit, it'll quickly identify that tons of them are bad with enough margin that you don't need to do any update with respect to those ones. There'll just be a few more borderline ones that you'll want to do updates with respect to maximize your margin. So, but usually only the top few will actually affect your update. And so that's why to make, instead of having to go through an exponential number of different solutions to get the best possible update, we can do as well or almost as well by just taking a certain number. Again, I don't know if it's 10 or 100, I'm not sure how many. Yeah, all right. So next I want to discuss the loss function. And so the motivation for this is, what if some mistakes are more serious than others? For example, in translation, often you won't get the original translation from the training set, right? Because there's lots of valid translations. However, maybe maybe this is a really bad translation, right? And this one maybe is not so bad, right? Maybe it's okay, or maybe it's, well, it's not good, but it's not nearly as bad as that one, right? And so we would like to really stay away from this point. Where staying away from this point, well, it's better to get that, but staying away from it isn't as important, right? So how can we introduce this into our model? Well, basically what we're going to do is we're just going to have a different margin for each of our points. We'll let it vary based on our point. And so okay. And so all we're going to do, we're going to change that to L of y, yk. So some loss that depends on y and yk. Now, to understand this better, so now we understand the margin is different. So let's say here, L of, let's call this y1 and call that y2. We'll just call that y, that's the correct one. So L of y, y1, maybe this is equal to 4. And L of y, y2 is equal to 1. Okay? So this is kind of 4 times as bad as that. So what's the algorithm going to try and do? So what this will do, if we only had one training example, okay, to give us an idea, because it's going to try and make things work for all the training examples. But if we only had this one training example, would make the margin with respect to y1 about 4 times bigger than with respect to y2. So the old way was, I'll do that in this color. The old way, if we only had one training example, ultimately our vector would be pointing something like in that direction, and it would be large enough to give us the margin we want. But now we want to be further away from this point, and so what I'm going to do is I'm going to draw this line, and now if I drew a line there and had a vector perpendicular, it would be twice as far away. So actually I'm going to put another point there. So this is 3/4 of the way towards y from y1, and I'm going to draw my line there. So this vector is perpendicular to that line to make the distance from this point and from this point the same. So now, and so that was for equal margins. Or I should say equal losses. So now that we got this, we're going to want to go perpendicular. We want to go perpendicular to that, and so that's going to give us a little tiny margin with respect to y2, but it'll give us, since this is 3/4 of the way there, this is 1/4 or 1/3 of that, so overall that distance is 4 times that distance, and so the margin for this will be 4 times bigger, and then again this vector will be long enough to give us the result we want. I'm not sure how long that is. Yeah. And so then it'll try and achieve this margin for all the different points in each training example, well, at least the k-best, and it'll also try and do this over all the training examples. So we might need to add other components to this vector to make it work for other training examples, but at least we need this component to make it work for this. We need this to make it work for this training example. And then, yeah, we can add other stuff that doesn't mess this up to make it work for other training examples as well. So that's loss functions. And as things get more complicated, like in machine translation, I think these are probably going to be very important. In machine translation, my understanding is pretty much you never get exactly the same sentence out. So you're just matching, like the blue score is, at least are some parts of the sentence matching up, and how big are those parts and how many of them are there. So yeah, if it's a really bad translation, then you want to definitely make the margin with that bigger. If it seems to be pretty good because it's fairly close to the original one, then maybe you don't need to make the margin this big. All right. So lastly, I wanted to go a little bit over factored Mira. So in structured prediction, basically we're going to ensure a certain margin for kind of each part. So that could be, I guess, one word in tagging. That could be whether you have a certain link in dependency parsing. Yeah. So this is with the k-best. For some parts, you could get a negative value, right? For other parts, though, you might get positive, and so overall, that might end up being your margin might end up being just fine. Whereas in factored Mira, if for one part the margin isn't big enough, then it's going to do updates. So this is kind of a stronger constraint. If it works for all the parts, obviously it'll work for the whole, but if it works for the whole, it doesn't necessarily work for all the parts, so we are, requiring updates when we might actually not need them. But the advantage of this is is another way to deal with the exponential number of possible solutions. Since we're just dealing with each part at a time, there's no exponential number of combinations. Yeah. Oh, so lastly I want to talk about the relationship between Mira and support vector machines. All right. So I don't totally understand this yet. So this is a support vector machine method, basically. I'm not sure if it's technically support vector machines, but we're going over all sentences and all solutions for all possible solutions for that sentence. And this is basically saying the difference in the dot products. I guess these could be kernels, something more general than dot products, but hold on. Yeah, so these are the scores. So doing the dot product with a vector, that's one way of getting a score. maybe this is, I think, just a more general way of writing it. So yeah, so we're requiring all of these to be greater than that. Using now the score probably depends on our weight vector, right? Because we're doing something like a dot product. So I don't know what that is. So we want to use as small a vector as possible, because if we're using a smaller vector and the dot product is still bigger than the margins we want, then really we've actually got a larger separation, right? So that's why we want to make this as small as possible. This is standard SVMs, so the difference in scores is bigger than a certain amount. So here, this is making this different for different points, which is, I think, different than the most basic SVMs. And we want that to hold for all training examples and all points. So this would be some big minimization that we'd have to do all at once, which might be quite hard. So we're doing updates. Now, on each update, we can't just minimize this, because then we'll destroy everything that we did before, all the work that we did before, right? Wow, don't know what happened there. I wonder how that'll turn out. So we don't just want to minimize this. So instead, what we're doing is we're minimizing the difference between or minimizing the size of the update, really. So I'm realizing that's actually a little bit different. This is a little bit different than Mira before. Mira before was trying to minimize that, but it constrained you to move only in the direction of the most recent vector. So instead of that constraint, we're just minimizing this. Yeah, so I found that kind of cool. I don't totally understand it. I don't totally understand the relationship yet. So I'll just quickly review the main points. If we could try to do one best Mira, but then once we're predicting the right point, then we've got no other point to work with, so we're not ensuring that we have the correct margin. And plus we might oscillate back and forth, where we just keep predicting those 2 points until eventually we're predicting the right point. So there's those 2 issues. And so instead of just predicting the one best point, we're going to predict a bunch of best points. 2 best at minimum to ensure that we have the margin. To make things more efficient, we can predict a bunch. And then we can just do 1 minimization to make sure that we do an update that's about in the right direction. It gives us the margin we want. So that's fairly aggressive, since we're making sure that we have the margin we want. At the same time, we want to minimize the change in our vector so that, oh, I messed up. We want to minimize the change in our vector so it doesn't mess things up for every other case, for every other sentence, say. And we use only the k best because if we try and work with all the points, there's just exponentially many, and most of them are just so far away from the correct solution, or they get such low scores anyways that they don't really matter. Everything shifted. And then some solutions might be much worse than others, which is why we want to allow our margin to differ based on the value of y. And so that's why we introduce this loss function. Particularly important in things like translation, where you rarely ever get the absolute correct answer. Well, I don't know if you rarely do, but I suspect no matter how much you train it, you're often getting something different than the original translation in your training set. Although I guess in some cases you could have multiple correct answers if you had that in your training set. And factor Mira is another way to deal with the exponential number of possible solutions, which is just by locally making sure that you make the right choice. Like whether you have a link between two words in your dependency parsing. However, this is a stronger constraint, which means that sometimes we'll be doing updates when we don't need to because overall the solution wasn't the best. But it does make sure that, maybe in the k-best, maybe there's one that wasn't in the k-best, but we should have done an update because of that one. Well, this will take care of that. And also, it seems like Mira is somewhat related to SVMs, in that SVMs try and minimize the margin. The original Mira was trying to minimize the margin, now we're trying to minimize the change. Or, the original Mira tried to minimize the norm of the vector we were using for prediction. This Mira for prediction tries to minimize the change so we don't mess up other predictions for other sentences. Too much? Yeah. Yeah, otherwise it looks pretty simple. We're just doing everything all at once with SVMs rather than online learning with a Mira type algorithm. Presumably we could also do batches where you do for all training examples in your batch and all y's, not all the possible y's, but your best k for each batch. And you want this to be greater than that, and you could minimize those concurrently, I assume. I'm not sure if there's significant advantages to that or not. All right, there you go.